This is a new chapter, chapter number 6. It's about registers and counters. So we have discussed in the previous chapter that what is a flip-flop and what is the role of a flip-flop. A flip-flop is a electronic circuit basically, which can store one bit of information. It could be 0 or it could be 1. We know that one, right? So flip-flops are of different type. It could be JK flip-flop, T flip-flop, D flip-flop. We studied, discuss all type of flip-flops. Now we are moving toward the broader application of flip-flop, which is registers and counters. So registers are basically the group of flip-flops which are capable to store more information rather than only one bit. We can store here more than one bits. Like we can have 2-bit register which can store 2-bit information. We can have 4-bit register which will be consisting of 4 flip-flops, and they can store 4-bit information together at once. And we can write 4-bit data there, we can read 4-bit data there, like that. On the other hand, counters are basically the special type of registers whose value will change or update itself. It is basically required to count an event. Okay, it could be a 2-bit counter which will count in 2 bits like 0 0 0 1 1 0 1 1. Okay, so this is the counter. So we'll discuss one by one what is registers and what is counter. So what register, as I just mentioned, give the definition, girls. A flip-flop are limited because they can store only one bit, but registers are not limited. They can store more than one bit. Okay, so we have, for example, if we have 2-bit counter, okay, it means it needs 2 flip-flops. Okay, for that. So 2-bit counter is a counter which have 2 flip-flops. So it counters, like if it is a up counter, and it will count like that 0 0. Next count will be increment by 1, yani 1 0. Next count will be increment by 1, yani 1 1. Next count will be 1 1. So it is like a counter which is counting in decimal, like 1 2 3 4, and with the help of 2 bits the maximum count will be 3. All right, so 0 to 3. So this is an counter example. All right. All right, so this is a count, basically a counter. So a register is an extension of flip-flop that can store multiple bits. All right, registers are commonly used as temporary storage in the processor. In a processor, inside the processor chip, it is there itself, so that it can, processor can temporarily store the data in the register, read or write fast because it is near to the processor. They are very fast, so processor can quickly access the data. You have heard about the cache memory. So cache memory is designed by using these registers, which is static RAM. Okay, so they are faster and more convenient than the main memory, because the main memory is far away from the processor, though registers are inside the processor. So it is very fast. More registers can help speed up the complex calculations. It is like that. So let's see now what register and how it is designed. So this is an example of registers, which is like you can see this is designed with the help of D flip-flop. These are, here we can see 4 D flip-flops. So these flip-flops are, now it is in a form of a register. I will call this one as a register. I will not call a flip-flop. So this is a register which is capable to store 4-bit information. You can see now. So there are 4 flip-flops. So 4 inputs, 4 outputs. So we can store 4-bit information there. we can read 4-bit information. All the flip-flops are connected to a common clock. You can see the clock there. Clock is connected to all, which is common. And by the way, this is a positive clock. We can see we can also have negative clock as well. Another control is their reset control, girls. This reset control, which is active low. Yani, if this reset value is here 0, whatever is the content of these registers, it is gonna be clear. It is gonna be 0000. Okay, this is external control which used to reset the content there. All right, so group of D flip-flops we can see here. This is synchronized. Meaning of synchronized is that it consists of a single clock. There is a single clock which is connected to all flip-flop, which means synchronized. They can store data. All right, let's see now within this thing. Try to understand how it is going to be stored the data inside it with the help of a waveform or with the help of timing diagram. So this is a clock, girls, which is connected to all four flip-flops. And by the way, if you look to the clock, this is a positive clock. Positive clock means this is positive age clock. Yani the information will update with the clock. And we know the characteristic of the flip-flop that whatever is connected to the input, the status will not change until we trigger the flip-flop. Yani until we give the clock. Whatever is the input, let it be. The stored value will not change. States will not change until unless you trigger it. So triggering method, which is shown here in this diagram, is positive gate triggering. And you know that positive age triggering, whenever there is a transition of in the clock, value will change from 0 to 1. At that time, flip-flop will trigger. So we highlighted these with the arrows. You can see any positive triggering here, 0 to 1, 0 to 1. So let's see now, assume some inputs, okay, which is the values of I0 to I3. So we assume some values of it. So what are the values? You can see here, this is what, this is 0, this is 0, this is 1, this is 0. You can see. But girls, you know that yani the states of flip-flop will change only on the age. Yani at this moment, this data will enter to the flip-flop. Before that, we assume that flip-flops outputs are 0. It is initial value. Always we assume initial values stored there is a 0, 0, 0. But what we are connecting to I3 to I0, it is given 0, 1, 0, 0. But it will not enter to the flip-flop until it triggers. So now the green highlighted lines here is basically showing the triggering moment. At that time, the values will change. So let's see now, this is the outputs. Yani A0 to A3 are the out, and initially all are 0, 0, 0, 0. All right. So what will happen at this trigger? I will explain with the help of this diagram. So let's see, this is the triggering here. At this moment, what will happen, girls? All before this trigger, all outputs are 0, 0, 0. But as I trigger, what will happen? I3 value will enter to the A3 and A2 value will enter to A2. I1 value will enter to A1 and I0 will enter to A0. So you see here A3 was 0. So A3 was 0 still. Now A2 was 1. So its value changed to 1 now. You see this one. Before all flip-flops states was 0, 0, 0, 0. Now it's changing as per the input. So here is a 1, A2. So A2 will also be 1. Now, what is the value of I1? I1 is 0. So A1 is still 0. What is value of I2? I0, sorry. I0 is 0. So A0 will be 0. So this is the value which is now the status of this register, like that, 0, 1, 0, 0. Now, this state will maintain until the next age come. And if even if during this duration, if you change the inputs, it will not affect the stored values there. Now you see what is the current values of I3 inputs. This is 1, this is 1, this is 0, this is 1. But see, it is not changing this value, it is fixed because of it is following the previous states before the age. Now next age is gonna become here. At this age, the information will update. All right, you see now. So at this age, the things will change. So I3 is 1, so A3 is gonna be 1. I2 is 1, so I2 was already 1, it will maintain its status. I1 is 0, it will maintain its status as 0 until next age. I0 is 1, so it will 0 change to 0 to 1 and maintain its status until the next age comes. So this is the next age, girls. And at this age, you can see what is the input value this time. 0, 1, sorry, this is also 0. Both are 0, 0. This is 1. This is 1 also. But can you see what is there? It is exactly same which is there. This one, this value, because it is updated accordingly. So what is the updated value here? This is like 1, this is 1, this is 0, this is 1. It will not change until next age come, and next age is coming right here, like this one. So at this moment, this will become 0, you can see, and this is what will be the 0 again, yani move to 0 this time. Next value is 1, it will change to 1. This is also 1, so it will maintain its status like that. So now these values are entered here like 0, 0, 1, 1. So the point is the values will update, or the flip-flops will update its status only on the age. Before that, no change will be happen. So this is here. These values are here now. Is it clear to all? The working of this 4-bit register, how the states are changing with every clock.
Yes, it's clear.
Okay.
Yes.
So, all right. So here the thing is, the data is entering parallel. Do you know serial and parallel concept? Serial and parallel. Parallel yani simultaneously, and serial yani one by one. So basically, if you look here, we are providing data parallelly. Parallel yani all inputs are applying to the flip flop same time. Output here is getting at the same time. So parallel input, parallel output we are getting here. Let's have an example. Rather than giving data, you're storing data in the flip-flop parallelly, we try to this time connect serially, yani bit by bit. Now all bit together 4-bit, but in serially, bit by bit data will enter, it will store. So next slide is about, which is serial register, shift register, what we call. So some arrangement to the previous circuit you can see here. Here what we have, yani we are not giving input to all the flip-flops. It is connected like that. The output of this flip-flop connected to the input of this flip-flop. Input of this flip-flop is the output of this flip-flop. Input of this flip-flop is the output of this flip-flop. Then we have serial output. And here we are giving input serially. So actual input we are giving here. And what happening? We are having a common clock. So everyone will trigger at the same moment. So what will happen? Yani for example, if I enter from here 1. So as the clock comes, this one will shift to the next state after 1 clock. The next clock, this will shift to here. After next clock, it will shift to here. After next clock, it will shift here. Yani, we know that with 1 clock, everyone will trigger same time. So if I say initial values of all flip-flops are 0 0 0. Correct. So with every clock, the data which you provide here as input, it is gonna be shift with every clock to the next flip-flop. That's why it is called shift register. Okay, and here we have example of 4-bit shift register, yani which can store 4 bits at a time and can shift every clock with every clock. Okay, so serial in, serial out shift register, because we are getting output serially bit by bit. Same with one modification, we can say serial in. So data is coming inputting as a serial, but output is same time. So which type of register it will be? If serial data input is serially but output is parallel. So this type of arrangement of the register is called serial in, parallel out. Can you see this one? We can take output parallelly this time. All output will be available like that. So we call this type of register serial in, parallel out. Okay, and connected to a common clock so that everyone will trigger same moment. So let's see an example of serial in, serial out shift register. Or see this one. So with the help of gain timing diagram, we are assuming that serial input here. So here is the input, right? This is the input, and this is the clock. So we try to understand with each clock how it is gonna be change. Okay, but first see what is the serial input. This value is 0, this is 1, you can see this is 0, this is 0 again, this is 1, this is 1 again. Okay, can you tell me which flip-flop you are giving this serial input? Serial input to all or to a particular only? Serial input.
All.
Where is SI? Are you connecting to all? We are giving input to this first flip-flop. This is flip-flop, the first one. Next one is basically the input for the next one is the output of the previous one. The input of this one is the output of this one. So this is serial input data which is coming here and which is given to this flip-flop only. And this value will shift with every clock to the next. So we assume that serial input is 0 1 0 0 1 1. Now initially all flip-flops are 0. So we are reading value of q3 q2 q1 q0 parallelly all together, and we assume that all the flip-flops initially have 0 stored there, clear, initially clear. So now, so this is 0. Okay, this 0 is present here. Now as the clock comes, can you tell me when I trigger it, where this 0 will go? To which flip-flop? Q3. So with the clock, what will happen? This Q3, yani this value of serial input will store inside the Q3. So let's see now. And at that time, same time, because everyone is triggering, so this 0 will enter here. But what about the status of this flip-flop, and this flip-flop, girls? Initially, we assume that all flip-flops are clear. Yani everyone is having 0 0 0 stored there. So as the clock comes, this 0 will enter here. Yani I will just replace with this one, right? Say a red one now. This is the enter here. Okay. So the 0 which is here, okay, now it will move to next flip-flop. Yani here, because this is connected here. So now it will be updated with this red 0. I'm saying this one. All right. And now this 0, what the blue one will go here and it will update with that 0. All right. And this one will go there and will update with that 0. And finally, this 0 will go out. So this is one clock. What will happen with the next clock? Next input is this one. It's like that. So see now what will be happening here as the timing diagram. So Q3, as I just mentioned to you girls, it is gonna be update with this value which is 0. So this will be here. Yani 0 will insert to Q3. But what about the Q2? Q2 will be having the value of Q3. Q1 will be having value of Q2. And Q1 will be having value of Q1. This is the arrow direction showing. So see the timing diagram. See, all are 0, 0, 0, 0 this time. But for the next clock, look here. For the next clock, girls, next input is gonna be 1 this time. Input is 1. So 1 will insert to Q3. And this Q3 value will update the value of Q2. Q2 will update the Q1. Q1 will update the Q0 because the output of 1 is the input for the next one. So with the next clock, Q3 will become 1. See now? And Q2 will be 0. Q1 will be 0. Q0 will be 0 because Q2 was 0, Q1 was 0, and Q0 was 0. Now, the updated values of this one is, this is 1, you can see, this is 0, this is 0, this is 0. So as the next clock will come, what will happen? The new serial input will go here and Q3 value will update the Q2, Q2 will update the Q1, Q1 will update the Q0 like that. So next clock will be like that. See, so this will be 1, this will be 0, this will be 0 like that. So with every clock, the data is shifting like that. Okay, are you getting this point, girls?
Yes.
Okay, so next clock will be now data will shift like that. So this is called shift register, girls. This is called shift register, and data is serially input here, and we can read it parallelly. Let's see this one. So the point here, like you can see, this was 1, the data here was 1. So with one clock it is shifted to Q1. The next clock from Q1 it is shifted to Q2. Next clock from Q2 it is shifted to 1, and after next clock it is shifted to 0. So you can see the value of the input which was 1. After one clock it reached to Q3. Next clock it reached to Q2. Next clock it reached to Q1, and next clock it reached to Q2. Yani from here to reach to here, it took 1 clock, 2 clock, 3 clock, then 4 clock, then it is here available. So serial input 1 by 1, it is like that. So this is shift register, girls. Now see, this is this given to you example, like we have initial value of a register which is 0, 0, 0. All right, now we have given a data which we wanna in. So with 1 clock pulse, this is clock 1. As I give the clock, so this one will enter here, and this 0 which was here will move to here. This 0 will move to here. This 0 will move to here because it's a shift register. This 0 will go out. Getting point? Yani it is gonna be 0, 0, 0, girls. All right. Now after next clock, what will happen? So the value which is here, it is gonna be shift here to the next, and the next one it is gonna be enter here, and this 0 will move here, this 0 will move here. They are shifting here, right? So 0 and 0. So this is the status of shift register after 2 clocks. After 2 clock. Now, third clock. with the third clock. What happened? Okay, next is it is gonna be out here. It is, I'm just writing completely here, 0 0. Now with that clock, this will go out, this will shift here, you can see this will shift here, and this will shift here. Now the next input will be here, which is 0, and it is 0, and it is like 0. So this is the status after 3 clock. This is the fourth clock. So you can see this will move to 0, this will move here, this will move here, this will move here, and the last bit will enter here. So you can see this is the exact data, which is 1011. It is now stored here, girls. It took 4 clock cycles to store that data, 1011. All right. So with the next clock open, whatever we stored here, it is gonna take it out. So if I give 5th clock, the stored information is gonna be out now, and it is gonna be shift towards right. So this is how basically shift registers work. It basically shift the bits one by one this way. Let's see one example, one question for that. It is like, so question may also come with that. The content of 4-bit registers is initially 1101. The register is shifted 4 times to the right, with the serial input being 101101. What is the content of the register after 4 shifts? So they are saying that initial value is this, and input is this. After 4 shifts, what will be the content of the shift register? This is the question. So we have given that we have a 4-bit shift register. This is 4-bit shift register. And the content is given to you, which is 1101. And what are they saying? The input to this one is 101101. Now they are asking you, after 4 shifts, what will be the content? Okay, so it is very simple, as I explained to you earlier. With every shift, what will happen? Data will move to next. Yani this will go out, this will shift to here, this will shift here, this will shift here, new value will come here. Yani 1 1 1 0. This one will go outside. Now with the next shift, what happened? This will go out, this will shift to this, this will shift to this, this will shift to this, and the 0 will enter here. So 0 1 1 1 0 will go out. So second, this is first clock, this is the second clock, now the third clock, third pulse. This one will go out, this one will go out, this one will be here, this one will be here, this 0 will be here, and next value is, which is 1, it is gonna be here, yani 1. So the after third clock, the value is 1011. Fourth clock, this one will go out, this 0 will be here, this one will be here, this 0 will be here, this one will be here, and next will enter now. So this is 1. So clocks, I can say the content of shift register is 1101. This is something. Is it clear to all of you?
Yes. Sure.
So same question I can ask, like, yeah. Any question?
We solve the several number for each.
Sorry,
It's like
again, what is that?
we solve each number for the for the flip flop.
Yeah, this is basically with every clock. This is, I write
Yeah.
number here, 1 2 3 4 5. It's showing with every clock what is the status. and you know that it is a shift register. So as the clock come, the content will shift to right. It's like that. So every clock, the bits will shift from left to right, left to right. So what is the update? I am just writing with every clock. So I need to know what is the status after 4 shift. So after 4 shift, this is the status. Actually, this is
Okay.
my answer.
It is stop
Okay.
on the fourth number,
Yeah, it is a stop. It is because of
not until the sixth number.
they ask after 4 o'clock. That's why I stop here. I can
Okay,
ask the
thank you.
question after 5. I can ask after 6. I can ask after 7.
Okay, clear now. Thank you.
Okay. So yeah, it is like that. All right. So this type of questions are possible related to the shift registers. Now move towards counters. Okay. So as I just mentioned to you, a counters, the role of counter, we know that you remember maybe abacus. This is used to count, but now this is a digital era. We have a digital systems which can count an event. So counter are a specific type of sequential circuit, okay, like registers. The state or the flip-flops value themselves serve as the output. Yani it will update itself. It doesn't require external inputs. Once it start counting, it will start with an value, initial value, and keep incrementing one by one. For example, if I have 2-bit counter, so how it will work? The initial value will be 00 state. It will increment by 1 and produce the next value, which is 01. So from 01, we will add to that one, this stage. Next state will be 10. From this stage, we add 1, and next state will be 11. And from that one, girls, it reached to its initial stage, basically. So this is the 2-bit counting. Start with 00, 01, 10, 11, 00. It is called up counter, which is basically counting upward. Initial value 0, maximum value 11. So the output value increases by 1 on each clock. After the largest value, the output wraps around back to 0. It goes back to 0. So it works in a circular manner, basically, this one. So this is what? This is state diagram. This is what? It is a state diagram, which is showing state transitions. So here we can also show this one, present state and next state. So because there are 4 states, we have 2 here flip-flops. We have 2 flip-flops, which is like that. State 00, next state is 01. Now next state will become the present state now, yani 01. Okay, from this present state, next is gonna be 10. Next count. Now this next will become now my current state, present, and from 10, next is gonna be 11. And this next state is my present state now. From this present state, I will to 00. Okay, is it clear how it is working? Okay, are you getting this? How this is working, how the counter is working? Starting with value, keep incrementing one by one and reach to maximum value. What reach to maximum value? It reached initial value again. So it is a counter basically. Now we will discuss next how can we design the counters, what are the type of counters, like that. So see now, counters. Why do we need counter? This is the first question. Why do we need counters in a digital service? May have three functions. First, timing. Yani building precision digital clock is an example where a low frequency 10 hertz signals clock cannot be achieved with the crystal oscillator. Actually, in order to generate frequency signals, we need oscillators. The role of oscillator is to generate the signals, waveforms, but we cannot get it up to very low, which is 10 hertz. We need to have a digital solution, which is a counter actually, which is used for the timing of it. Like you said, in digital clock, we have a second counting, which start with 1, 2, 3, and which reach to 59. And after 59, it reset to 00 again. And once you complete 60 seconds, the minutes will increment by 1. So second thing is sequencing. Yani starting of a rocket motor is an example where emphasizing the fuel pumps or energize the fuel pumps, ignitions, etc. must be follow a critical sequence. Yani it should be done first. When it is finished, do for next. When it is finished, go for next. Like fuel must pump must be energized first. When it's clear, then we have to initiate the ignition, then move to next. It is happening in the digital clock also. If you remember, the very first here is what seconds. Once seconds reach to maximum value, it triggers the increment the minutes. Once minutes reach to maximum value, which is 59, okay, it will increment the what hours. So this is where we use sequencing purpose. Next is counting. We use for the counting as well. Measuring the flow of traffic on a road is an application in which total number of vehicles passing to a certain points need to be counted. So counter is also used to count an event itself. Yani I want to count how many cars are passing, within for example, in our 1 hour through this point. So I can place a counter circuit over there. There will we need a sensor somewhere. Sensor will sense the presence of some object, and it will send a signal to the counter, and the counter will keep incrementing accordingly. So this is a counter circuit. So applications of the counters, hope it is clear to you. Any question related to the applications where we use it and why do we use it?
No, thank you.
All right, now see next what counters, what are the type of counters, girls? Counters are basically broadly two types. Okay, what is that? Ripple counters and synchronous counters. Ripple counters are also called as asynchronous counters. This is called synchronous counter. See now. So the example which I just give you for the registers also, that was synchronous. Synchronous means a common clock. Synchronous means common clock trigger all flip flops. When I say ripple counters, yani another name is asynchronous counter. So it is not going to have common clock, but the output of one flip flop, any flip flop output, basically to trigger the another flip flop. We will be having common clock, but the output of one flip flop is going to serve as a trigger for the next state. It is what ripple counter is basically. But in synchronous counters, we will be having common clock. So one clock will be triggering to all flip flop. So we will discuss one by one. Like first we'll discuss the ripple counter and we will discuss the synchronous counters. Okay. So ripple counters or asynchronous counter is one in which each flip flop is triggered by the output of the previous flip flop. So keep in mind, this is important point. So the output of one flip-flop is going to trigger the next state, like that. Because of it, what happened? It is limited. It has limited operation. Why? Because all is not going to trigger same time. In order to trigger one flip-flop, it need to wait the output of the previous stage. So that's why speed is less here. It is not as fast as the synchronous counters. Asynchronous counter are also called as a ripple counters or asynchronous counter. I already told you. These counters are easier to design. It is very easy to design. It has fixed design method. Are constructed using minimum hardware. So I am starting now to explain you how can I design asynchronous counters. And see, counters could be up counter, counters could be down counter. Up counter means which will count in upward direction, like starting with 0, then next will be 1, next will be 1, next count will be 2, next will be 3. Then let's see, if it is a 2-bit counter, maximum count will be 3, and it like that. But if I'm saying down counter, it will start with the maximum value like 3, 2, 1, then 0, like that. So one by one we will discuss about this one. So let's see first the design of repeaters or asynchronous counters. See this one, and as I told you, it has fixed design method and it is easier to design. So we are going to discuss 2-bit ripple counter here, 2-bit. So if it is a 2-bit, it can count up to any 2 like that. So first count will be 0 0, second count will be 0 1. It is up counter, by the way. I will tell you how can we design down counter. So next count is gonna be, what will be the next count after 1 1, girls? If it is 0 0, 0 1 1 0 1 1, what will be the next count after that?
0
After
0.
1 1, 0 0, because it works in a loop, basically in a rotation manner. Will reach to 0 0, then it start counting again. It is like that. And let's assume that these, as per this circuit, this is Q1, another one is Q naught. Q naught. What is Q naught? LSB and MSB, if you remember. So Q naught is the least significant and Q1 is the most significant bit. All right, let's see now. Here in Q1, can you observe this pattern? What is the pattern here? Not for the Q naught only. Can you see something here in this column? Notice something, the value, like the first value is 0. What is next value?
1.
So is there any pattern here?
0 1 0 1 0.
Yani complementing here. Yani the next value is the complement of the previous one. Next value is the complement of previous one. Next value is the complement of previous one. Next value is the complement of previous one. Am I right?
Yes.
And do you remember the JK flip-flop? There is a stage in the JK flip-flop when J and K both are 1 1. What is the next value at that time? JK. If this is J, this is K, and this is QT plus 1, yani next value. So how we write the truth table for this JK flip-flop, girls? If both are 0 0, 0 0, if it is 0 1, I'm just writing the truth table, asking you truth table for JK flip-flop. It is 1, it is 1. So when both are 0 0, which state is this? Do you remember? No change. When it is 0 1, which stage is this? Reset. This is 1, set. And this one 1 1, when both are 1 1. What is that one? Toggle state. What is the meaning of toggle state? Yani it is basically the complement of the previous value. Complement of the previous value. I can write it like in place of toggle. What is that? Qt plus 1 will be Q complement of the previous value. So the point is when both J and K are set to 1 1, they are 1 1. The next value will be the complement of the previous value. See now design, girls. Okay, in this design, you can see here we have two flip-flops. Flip-flop 0, flip-flop 1. Flip-flop 0 is giving me LSB, least significant bit. You can see Q0. Flip-flop 1 is giving me Q1, yani most significant bit. You can see here in the counting here, Q1 and Q0. And here we are giving clock to the least significant, flip-flop, which is FF0 clock. It is connected here. But J and K is connected to high, yani 1. J and K, another one is connected to high 1. Why we are connected to high? So that the next value will be the complement of the previous value. Getting point? Once they are connected to 1 1. So J and K both are 1. Whenever whatever is the previous value, next value will be the complement. And now we are connecting clock to the first one, but the second flip-flop is not connected with the same clock. Why? Because it is a synchronous design. So only clock to the first one, but the output of this least significant count is gonna be served as a clock for the next one. All right, this one. Now, how it is working, girls? See this time. So initially flip-flop set to 0 0. Both are 0 0. All right. So clock is coming for this one. As the clock, let's try to understand with this timing diagram. We have a clock, this clock, and we are giving this clock to this FF0. Okay. So this is the output of FF0, clock 0. And try to understand that which type of clock is this? Is this negative or positive clocks? Negative clock or positive clock?
Positive.
This is a negative clock, which is showing that it is a negative age triggered. It means the triggering will happen when the clock value will change from high to low. High to low, which is here, high to low. This is the change. Similarly, this is changing from high to low. Arrow direction is saying the value of clock, high to low. That's why it is negative, like this. All right. So now, as the clock comes, the status of both the flips are basically 0 0. All right. So this is 0, and you can see 0. Q0 0, Q1 is 0. As the clock come, so what will happen with this Q0, girls? Because both are 1 1 set to 1 1. So the next value is gonna be complement of the previous value. So it will make 1. But this clock is only for flip-flop 0, not for flip-flop 1. So it will change the status of flip-flop 0. Now 0 will become 1. We will discuss this one on David, this second way, which is for flip-flop 1. So I am explaining the flip-flop 0 first with the help of this clock, because this clock is given to flip-flop 0 only. Now, next age come. As the next age come, the value stored there Q0 is 1. So what it will become now? It will become now 0 because of toggle stage. N K connected to high all the time. So they will toggle always. Now, with the next pulse, what will happen? 0 will become 1. Next clock, it will become 0. Now, you see what is the clock for FF1, girls? what is triggering for flip-flop 1? The output of FF0 is going to trigger to the FF1. Means this is gonna serve as a clock for this one. So I will not look this one for FF1. I will look this one. And again, this is bubble there. It is a negative triggered. Means is that it will trigger only on the negative edges. Yani this is change from 0 to 1 and now 1 to 0. So here it is a change. So here the will change. Again, next change is there. So flip-flop 1, for flip-flop 1, the output of flip-flop 0 is basically. So now initial value of FF1 is 0. It will be 0 until the age come, and you see this is the trigger. So this will no change here. Now as this trigger come, because it is again connected to J and K, both are connected to 1 1, it is gonna be in toggle stage. As yani toggle stage means it will change its value 0 to 1. So this 0 will become 1 here, and this will maintain its status until the next trigger. So next trigger is here. So this one will continue 1 again, and 1 it is the next trigger. This will become 0 now. Okay. Now can you read like Q1 Q naught? This is Q1, this is Q1, and this is Q naught. Read the values. It is like 0 0. Write 0 0. Read it here 0 1. I write it like 0 1. Next read it 1 0 1 0. Count the next value 1 1. Write it like that 1 1. What is next value? 0 0. Can you see the pattern? Now like this one, how it is counting basically, what are the values of the outputs. So it is starting with 0 0 0 1 1 0 1 1 0 0. So which type of counter is this? Up counter or down counter? It is counting upward or downward?
Downward.
Don't see the arrow direction. It is down, it is downward. It is counting upward, means it is counting 0 in decimal. Next count is 1, next count is 2, next count is 3. So it is counting upward, yani incrementing the values, moving towards the higher value. It is called upward. So this is up counter. And after reaching to the maximum value 3, it is resetting to 0 again. This is the design of a 2-bit up counter. Up yani it will start with the lower value, which is 0 0, and it reach to maximum value. So this is 2-bit ripple counter which has 4 states. A counter with n flip-flops can have 2 power n states. Because we have 2 flip-flops here, it means 2's power 2, yani 4 states are possible. For example, if I have 3 flip-flops, so 2's power 3, yani it will be having 8 states. So that counter will count from 0 0 0, next count will be 0 0 1, and it will reach to 1 1 1. The next count will be 0 0. So it can count 8 different states like that. A number of states count is known as mod. Known as mod, or what we call modulo number. Okay, so number of states. So how many states we are having here? As I just told you, we have 4 states. It means is that the mod of this counter is 4. Okay, mode of this counter is 4, right? So it's called mod 4 up counter. Mod 4 up counter. All right. So this is the design with the help of JK flip-flop. We can also design flip-flop with the help of D flip-flop, with the help of T flip-flop. And you know, with the help of T is very simple because T is the upgrade version of JK. If I want to design the same with the help of T, what I need to do, rather than JK, I will just use two flip-flops, which is T, T, and just connect this one to high. This is high, this is high, and this is connected to the clock. This is clock, and this is the output of this. And it's same, everything is same except bus input, which is high, high. So we can design it with the help of T also. So we are stopping here, and next slide is showing the same thing here, which I just showed, yani with the help of T flip-flop. Could be designed with the help of D flip-flop. All right. So I will continue next from the slide 16, inshallah. So just stop here.